So with that, let me get started. So what I want to focus on today is this water graphs. I think if you're attending this webinar, I'm going to assume you know about graphs, but there might be a couple of people who don't. So I'll just give a very quick recap on what are graphs and why they're relevant. And then I'll go into the core of the presentation is designing a database for graphs and the language for working with graphs. There is specifically this new SQL syntax in the SQL standard that was published in 2023, June 2023. So we'll talk about that. And then I'll talk about performance and scale, because often the question is, if you have graphs and you're trying to work with that with a language like SQL, how will it perform? So I want to try and address that question, and then we'll end with some resources. So let me start with water graphs, and let me also say that you can post questions in the Q&A box, and Denise, my colleague, will be happy to answer, or be interesting questions we can answer live. So please feel free to keep the questions coming. We would like to have an interactive session if possible. So water graphs. So if you basically over the last few decades, we have seen that organizing data as rows and columns is a very efficient way of retrieving data. But if you want to ask questions such as, is data entity A connected to data entity F? You need to traverse links through data that is represented as tables. And if you were to do this in SQL, it would typically be a bunch of self-joins. So those types of queries are not immediately intuitive when you're only looking at a storage structure that is rows and columns. So what happens there is when you actually model that same data as a graph, when you have a graph view of your data, you can answer questions such as, is A connected to F, much more intuitively, because the connections become more obvious. And that's what the graph data model is all about. How do I traverse connections in my data? How do I analyze my data in a different way? Because these connections between data is made more explicit. And there are any number of use cases where such queries add value, where you're traversing connections in data. One is in a social network where the connections are more tangible, such as who is following whom, who reposted whose post, and things like that. Those would be the connections between the data entities. And then maybe less tangible or implicit connections, such as in a bank transactions. So let's say my friend and I go out for lunch, and then I use a payment solutions app to transfer money from my account to my friend's account. That is a connection between our bank accounts. It's more implicit. It's not a physical connection. But it is a connection nevertheless, because there was a transaction between our bank accounts. And that, interestingly, has a lot of applications for the financial services industry, where they use patterns such as that to see how money is moving around, to see whether there are any anomalous patterns that would detect fraud, and so on. So analyzing your data based on these connections, explicit and implicit, kind of opens up your data to new discoveries. And graphs are really good at finding things like, okay, are there direct connections? Like I here is direct connections. And also the interesting thing about I is it's a highly connected node in your graph. You have lots of nodes in this graph, but I has 3 incoming connections, so it's highly connected. And which are the direct connections to I, and which are the indirect connections to I, like 2 or 3 hops away. And that is particularly, that's can be done really easily with graphs. I have recognized that because of graph queries or running graph algorithms, I've recognized that I is a highly connected node. And then I want to see everyone that's indirectly connected to this node. So queries like that, graphs make that simple. So how would we go around designing a database for graphs, for doing these types of operations efficiently? So over time, of course, we have relational databases, though they are like 4 decades old. And then over time, we've had newer and newer data types. We've had documents, we've had graphs, we've had geospatial data. We've had many different kinds of data types. And one approach is to have what we can term as the storage-centric model, where you're designing your storage from the ground up for doing those particular operations extremely efficiently. Like in the graph case, if you're traversing links, you make those you design your storage so that those operations are really efficient. And if you look at JSON, if you're looking at a document store, you design a database where you make those particular operations efficient. So from the ground up, you design a database specifically for that data type. But that has all kinds of challenges, such as developers need multiple skills because different databases will have different skills. There might be different languages that you need to use. And the biggest challenge of them all is that fragmented data makes applications complex. So if I have my data in a relational database, and then I need to view it as a graph, if I have to move it to another database, right there I'm introducing a lot of complexity in my manageability. Like when data is updated, typically business applications will be using relational databases. They would be updating, let's say, data regularly. If you want to keep data in sync, you have to keep synchronizing between your database and your relational database and your graph database and so on. It just increases costs a lot. So we keep routinely talking to customers who say that, oh, okay, we had these specialized databases, but now we are not, our costs are just exploding. So we just want to see how we can do this differently. So the approach of Oracle has been to have a more use-centric model in the sense that you store your data once in whatever format is efficient for that database, but then you interpret it or use it as needed by the application. So if your application wants to work with JSON data, you interpret the data that you have stored in the database as a JSON document and use that in your application. Or if you want to use it as a graph, you interpret the data as a graph, like you have a graph view on your data, and then you use that in your application. So this is termed as either the multi-model database or polyglot or the converged database. The term Oracle has been using is the converged database, where you're bringing in many different types of data, many different workloads, and many different types of operations like analytics, OLTP, etc., all of them into one database. And when you think about it, this is not at all a surprising development. I mean, we are moving towards things like, for example, our phone. I shouldn't say once upon a time, not so long ago, we had a separate camera, we had a separate phone, we had a separate device to listen to music, and we had a separate device to tell us the time. We had a watch, and these were all distinct devices. When smartphones emerged, all of these, your smartphone could do everything and do everything quite efficiently. It's not slowed down because it's doing all these different types of things. And that's the similar analogy with the database, where you are doing different kinds of operations with your data. Why not simplify and have one database rather than having different databases that will just fragment your storage and just make your applications more complex? So in database 23C, so the converged database is not a new concept. We've been talking about it for a while. In Oracle Database 23C, which is now available on the Oracle Cloud and will soon be available everywhere, we have really taken this to the next level. So we say that you can store your data in one format, which is typically kind of like a normalized relational form, because that is the most efficient way to store your data and to run many different kinds of queries. And then one app can use that data as relational, And another part of the app can treat the same data as a document, and yet another part of the app can treat the same data as a graph. And so this is what we have been doing in 23C. We just added some more components to kind of take this to the next level. And one key technology is the JSON duality views that are part of Oracle 23C, where you can interact completely with JSON data from your app. You can read data as JSON, you can update data through JSON, you can use an API that's specific for JSON documents, or you can use SQL. So you can completely interact with data as JSON, and the underlying storage is optimized. Like I said, using the normalized form that has been used for the last 4 decades, which has many advantages, such as data is never duplicated, data is always consistent, and certain things like concurrency, concurrent updates are really easy to do and really efficient to do with that very mature storage model. So what we added is this ability to interpret data stored as tables as JSON without any loss in performance. And in fact, we are faster than lots of than native JSON databases. And similarly, we have taken that approach for graphs as well, where a graph is like a graph view of data. So you have tables, you have your business data in tables. You can create a graph view of this data, and then you can run graph queries to understand the connections between data, to analyze your data as a graph, and so on. And once again, to emphasize, there's no data copy. Data remains in its source table, so data is stored once, not multiple times. Synchronization is not an issue. And then you can then insert, update, and delete into underlying tables. That is instantly reflected in the graph. You don't have to wait for synchronization to happen before your graph gets updated. And the database is naturally, when you're storing data as tables, is naturally very good at fast concurrent updates. And Oracle database has been doing this for 4 decades, where it can support thousands of users running tens of thousands of queries. Like we have benchmarks, the TPCC benchmarks, which just show hundreds and thousands of queries running per second. So these, and you can update data as you are querying them. You have all of these logs, things in place. So things are really, really very mature in that technology. So you can now use graphs with operational workloads. Because it's just built on the Oracle database, which is designed for various things, including operational workloads. And now graphs can be part of that. So the language, now we need to look at what would be the language for such a database. All right, so we have a database, we have this graph view on data. What is the language we will use to query this data? That's the interesting. That's the next question. So property graphs, there have been a few, I should say, open source ways of querying property graphs, but none of them could be considered as standard. So we began to hear from the developer community that they would really like to hear from, they would really like to see capability added to SQL, which will just make graphs accessible to anybody working with any kind of database. So we worked, along with other vendors, we worked with the ISO committees that work on SQL, and in SQL 2023, published in June of this year, there's a new part 16 that includes syntax for property graph queries. So you can use SQL to, if the standard is implemented, you can use SQL to work with graphs. So the standard includes the syntax for DDL, there's a data definition language that is to create a graph, drop a graph, and so on, and also syntax for querying graphs. And we'll look at a few examples. And So when you create, let me just take a couple seconds to talk about what we mean by the graph view, because for those of you who are just coming from the graph world, like we often talk to people who come from the graph world, and it takes them a while to wrap their head around the fact that, oh, I can create a graph view on my table data. What does it mean? So to kind of explain what that means, here are two sample tables, bank accounts and bank transfers. And this has an ID column, which typically would have a primary key on that column. And this ID column is connected to a source column and the destination column probably through foreign keys. So if there's a foreign key constraint between them, then you would know that every ID that's in the source and destination column here that represent money transfers between two accounts would be in this column here. So the bank accounts table has information on the ID of the account, the name, the balance, and so on. And the bank transfers information has information on which account transferred money to which account. So if you had foreign key constraints, you would not have accounts in the bank transfers table that do not appear in the bank accounts table. But you can create a graph with or without these foreign key constraints. But I just had these arrows to indicate that this ID is connected to these two ID columns. So when you have this table, what happens here is every row in the bank accounts table can become a vertex in the graph or a node in the graph. So we have the ID1 that becomes a vertex or node in the graph, and the name and the balance and other information you have in the table can become properties of that vertex. So every row in this table becomes a vertex or node in the graph. And then when you look at the bank transfers table, that contains the relationship information, contains information on which account has transferred money to which account. Those become edges. So every row in that table becomes an edge in the graph. So if there's an account transfer from 1 to 2, that's a connection between 1 to 2, and the properties here become properties of that edge. So, and as you might have inferred by now, so each table typically is associated with a particular label, like you have a vertex label, you have an edge label to tell you what type of vertex label and edge whatever vertex and whatever edge you have in the graph. So typically one table is associated with one label. So here we have we have only two tables. So we have one vertex table and one edge table. So that's how conceptually you can map the data from a table into a graph. And then let's see how we would create this graph. So every time, like I said, every row in the bank accounts table becomes a vertex. And every time there's a cash transfer between them, it becomes an edge. So the syntax as specified by the SQL standard, looks something like this. So you specify as a vertex table, the bank accounts table. You specify the key. If you have an index on this key, it would make your queries run faster. And then you specify the properties, which are the columns in the table. Then as the edge table, you specify the bank transfers table. And you have a key, and then you have the source key and the destination key. So the source key is a value in this column that refers back to this vertex table. And similarly, the destination key refers back to the vertex table. And then you have the properties again, which are the other columns in the table. So typically, when you're creating a graph from tables, this is just like an exercise in thinking about, okay, what are my edges? What are my vertices? Where typically the data entities, and then what are the relationships between them that I model, and which tables can I get them from? And those become the edge tables. And there might be some of you who don't think in terms of tables and you just want to start thinking in terms of a graph. I mean, that's possible as well. I'm just explaining this to highlight how we have a graph view on data. So when you have data in tables, how we can create a graph view on it. So here's the graph name. the tables holding the vertex data, table or tables holding vertex data, table holding the edge data. And then, as I was saying, the column values become properties. And then you have the source and the destination keys. And this is as defined by the standard. And you can also, if you have an index on, let's say, the source and the destination columns here, which are the source and destination for the edges, that typically helps performance significantly in the Oracle database. So next, let's look at what the query syntax looks like. So you might recognize this match clause if you run other graph queries. You would recognize this match clause, or almost all graph query languages have this something like this to represent a pattern in a graph. So anything in parentheses is a vertex variable, anything in square brackets represents an edge. So here I'm just saying, find me edges, find me all edges in this graph that connect any two vertices or nodes. And then I'm projecting. These are the columns that I want to be returned as results. I want to find basically every bank account that has made a transfer to another bank account. And visually, it will be something like this. So that's to explain the basic syntax. And you can see here you select. These are all SQL constructs. Graph table is a new syntax that is used to say that, okay, this is a graph. Bank graph is the name of the graph. And then we have the match syntax. And we can look at another query. Everything else is similar, where you say you have the select, you have the graph table with the graph name, and then you have the match. And the match clause is a little more interesting here, so that you want to say, find me all accounts that have transferred money to other accounts 1 to 3 hops away. So not just looking at direct transfers, but looking at transfers 1 to 3 hops away. And these are the kinds of things that folks looking to detect fraud in financial transactions are looking to find out. Is there, who are all the people that indirectly connected to these accounts? I want to see whether there are any spurious accounts connected that money has been transferred to, and so on. So 1 to 3 can be 1, 2, or 3 hops, and those are the kinds of things that the new SQL syntax helps you specify easily. And then here's an example where we're saying, if you just focus on the match clause here, we're saying I'm starting with vertex source and ending with vertex source, and this is exactly 5 hops. I'm looking for cycles, so the starting and ending with the same vertex means that this is a cycle. So I'm looking for cycles in the graph that are exactly 5 hops long. And that's something also banks are very interested in finding out, is money moving around in a cycle, because that's, depending on their business, it could be something to flag that they should look at more closely. And as you know, bank graphs are really good at doing that. And then we also can visualize these results. So we have a lightweight tool for developers to use to visualize the results. In this particular query, we're looking at, I'm saying, okay, we have a where clause here for 387. So I start with 387 and I'm looking for 2 hops. So account that are 2 hops away from 387 is what I'm looking at, and I'm running this in SQL, and then I'm able to visualize these results. So you can see that you can run all of these graph queries from within SQL, like in a SQL context. And you can add lots of things. You have a where clause, you can have order by, you can have various other SQL functions and SQL operators. You can combine that with this query. So other graph query languages will have that too. The difference being the other graph query languages might have to implement all of this from scratch. We're just building on SQL. SQL already has all of this. We're just kind of adding the graph pattern syntax to it. So this is, again, published in SQL 2023, and we are implementing this in Oracle Database 23c. And we're going to keep adding to this as we have newer and newer releases. So the big question then is performance and scale. Often people will say that, okay, if you're really using one storage format, which is like based on tables and is normalized. How can you do graph queries efficiently? Because you'll have to do lots of joins under the covers, and that doesn't really scale well. Well, that might be true if you are just looking at a graph query as joins, but what we have done is we have really added stuff to the database kernel to make some of these traversals fast. So we're not just doing simple joins, and even joins have improved in performance. But because we are natively implementing this standard, we have really made it, we have focused on making these operations fast, the graph operations that you need in a graph. So here are some sample numbers. This is still ongoing work. So we haven't published this yet, but this is ongoing work. So we took some of the queries from the LDBC, the Linked Data Benchmark Council, and we ran some queries. And this, what I'm sharing here, is from the LDBC interactive short queries. They are simple queries, but you'll be surprised to see that many customers are just looking for simple queries. I mean, they're running queries on their data, and they have a graph. Maybe they want to traverse a particular path, and they just want to add that to the graph. So I think in the LDBC interactive short queries, queries 2 and 6 include a multi-hop path. And actually, the benchmark states that find all paths. And we see that in the data, there isn't anything other than 9, which is why I say 9. So you're basically going up to 9 levels in some of these queries. So here are some performance numbers from that. And I just want to highlight that these numbers are in milliseconds. So these are sub-millisecond queries for the most part. So when you have the right indexes on, let's say, the vertex ID columns and then the edge ID columns, that you can get extremely high speeds. I am using a new machine. This is a good machine. That this is one of the Oracle Exadata boxes. We have a good amount of memory, so the graph can be cached in memory. But the point remains that we are able to get sub-millisecond query times. And these kinds of numbers really put to rest the argument of, can an Oracle database scale for graphs? Because Oracle database is no longer just a relational database. It has evolved to support many different data types, and I'll come to that in a second. So these are SF10 numbers. Then we have SF100 numbers, where the graph size is 0.3 billion vertices and 1.8 billion edges, the same machine. And once again, sub-millisecond per query times. And you can see here again that sub-millisecond query times. And Q2, of course, is not sub-millisecond, and that is one of the queries which has multiple hops. And there are that does take more time than other types of very simple queries, but it's still under a second. So you have sub-second queries for this very large data graph of nearly 1 billion vertices and 5.4 billion edges. We see that the performance is remarkably consistent. And that is because if you use the right indexes and the right techniques at your storage layer, it's just going to be extremely fast. You're only reading the data that you need. You're not putting unnecessary data into memory, and then things can be extremely fast. So to show how this would scale, I just plotted the SF100 and SF300. That's the 0.3 billion vertices versus the 1 billion vertices, but 3 times in size, just to show how the performance changes for all of these 7 queries in the set of queries defined by the LDBC interactive short benchmark. And we can see that the performance is remarkably consistent, because once again, if you're using an index, you're only reading the queries, the data that you need. If your data is stored in the cache, everything is in memory. So these are all the reasons how we're able to get scale even when we are doing graph traversal queries in an Oracle database in what is incorrectly, I think, termed as only a relational database. It's no longer just a relational database. And there have been lots of innovations in databases in general and in Oracle database in particular to make these kinds of queries fast. Like I said, talked about joins and what makes joins faster. We have all of these fast parallel joins, special structures to do this fast in memory, parallel recursive with. Partitioning. Partitioning has been a great innovation in Oracle, where you prune data at a very basic level and only use the data that you really need, and compression to give compact structures. And then when you're using an Exadata box, we have the storage level indexes that you're only reading the data that you need. So you might store data in tabular structures in a normalized form for other efficiencies. You can also do graph type operations extremely fast. And that's one of the key points I want to make today. And the thing about these relational databases is that they work very well for set-oriented queries. So when we decide that we want to go, if we decide we want to go to a native graph database that's good with graph queries, it then starts becoming inefficient for operations like this, right? So if you want to do aggregation, or you're just reading large sets of rows, relational databases are just, again, built on decades of technology, and they just do very well with those types of things. So instead of having to design all of this in a special purpose graph database, what we have done is we have taken what graph queries need and incorporated that into the Oracle database. And the combination is really powerful. Syntactically also, you can see here that everything is SQL. It's only the graph part of it that is new syntax. That's the graph part. That's the graph part. So rather than having a whole separate graph query language, we're incorporated in SQL, working with the standard bodies. So you're just able to plug graphs right into SQL and leverage all the advantages of SQL or relational data, and combine that with doing your graph operations. So if you look at a query, just one example of a query 7, we find here again you have this graph pattern within this larger SQL query. And we've been doing this for a while. I just wanted to add this one slide here to highlight that we also support RDF graphs, which has been a standard, I think, almost for 2 decades. The W3C came out with the RDF standards that are now quite popular with knowledge graphs. And there's a Sparkle query language for querying RDF graphs. And we had a similar approach there as well. There was already a Sparkle standard. So we said, okay, let's put a SQL wrapper around it. For the property graphs, we actually worked with the standards bodies to say, okay, let's just add syntax to SQL itself. But this results in a lot of dividends, and we see a lot of customers say that, oh, I need to do something. I need to use an order by clause, or I need to do some data cleansing, or I need to do some other operations that I can do really well in SQL. I can just use SQL for that and use graphs only when I need to use graphs, rather than trying to do everything within a special purpose graph database. And also with this, when we are doing this in SQL, running property graph queries in SQL, you can, the output of a graph query can be a table. So you can combine with other relational tables through, let's say, a join operation. You can query a relational table and then combine that with the output of a graph query, which also results in all kinds of interesting options, especially to combine with other things that the database supports, like geospatial support, JSON support, etc. And here's an example of working with JSON. So if you have JSON data in your graph, and JSON value is a database function for retrieving specific values from this JSON document, you can include those database functions along with your graph query. So here I just have a simple pattern in my graph query, and I'm just including database functions. So you can add any or include any database function in your graph query. And then finally, there is what we call, at least I like to call, the staying power of SQL. And this is something that we have observed. I mean, Oracle has been in business for many years now. Relational SQL was huge at the beginning, and then object databases came into being, and everybody said, "Oh, object databases will solve the problems that relational databases could not solve." And what happened was relational databases saw that this is something that developers need, and they evolved. They evolved into having separate native special purpose object databases. They evolved to say, okay, you can do object kind of operations in your relational database. Then there was the XML boom, where there was lots of ways of saying, okay, we need special purpose databases, but once again, SQL evolved. SQL has evolved for JSON. And if you look at big data, for instance, I mean, there's a lot of interest around using Apache Hadoop and other technologies for working with many large data sets. But finally, they also end up using SQL, like if you use Hive or all the other languages that you want to query your data, they're all either SQL or SQL-like, because it's just easy. I mean, the declarative power of SQL is very powerful for doing things very efficiently. And now we have graphs where you want to traverse links or pointers in your data. And once again, SQL is evolving to accommodate that as well. So I think it's not it should not be seen as an either or. Okay, I want to see whether I want to use relational or graph, but to see how we can use the database that you can do all of the things that you need to do together. And I guess SQL has really prevailed over decades, and I think for a good reason. For data management, it's really useful. And customers have all of these expectations that they want to ask OLTP, that they typically ask OLTP systems. If they're modeling the inventory as a graph, they might have constant updates and reads, like multiple updates a second, multiple queries a second. They want to be able to do all of this in a graph. It becomes harder if you need to synchronize between databases, and you have things are very real time now. Data is being constantly updated, so you need a database that can support this rate of updates, this degree of concurrency, and so on. And you cannot start saying, okay, I start having problems after a few vertices. We need to have the same level of service that you expect from a mature relational database. We want to make that available for graph databases as well, because no one really wants to sacrifice all the data management advantages we have really learned over the decades. So we have really focused on the ability to have graph analytics along with your OLTP transactions in your data without sacrificing any performance for graph queries. So that's, I think, one of the key things that I want to convey here today. And we have graph customers in a variety of industries, financial services, manufacturing, telecommunications, and more. So, and especially enterprises, for them, lots of these things like security, high availability are very important. So it's helpful to know that there is a trusted name behind those requirements that can also now work with graphs. So the key takeaways here, I think, is the key takeaway is to remember that relational databases have evolved. So when I keep saying sessions or blogs which say that, oh, relational databases can't really run graph queries, I mean, that is really not the case, because the databases, like Oracle database, is no longer just a plain relational database. It has evolved over the years to be able to query many different types of data at very high speeds, and with graph they shared some numbers, while keeping all the maintainability, security, and high availability features that one expects from a database. And with 23C, we're taking it to the next level, the concept of you store your data once in an optimized structure and then use it in any representation as needed by your application. So I really like this slide, which I borrowed from, I think, one of our executive sessions, where if you're using your phone, that's your converged phone. It just takes all of these different things that you used to do together with multiple devices, and it does it all with one phone. Similarly, you can do all of these different things with one database. And you can try this for free. If you want to try Oracle Database 23c, you can get a version, either a Docker image, or you can try. There are other options. If you just go to oracle.com/database/free, you can use this. You can try some of this functionality. And if you have access to, let's say, 19c, I kept talking about Oracle Database 23c. If you have access to 19c in your organization and you want to try some of this technology, you can. Almost everything that I said is available, except you have to use the PGQL language, not the SQL language. The SQL support comes only in 23c. But the PGQL language is very similar to SQL. The difference is it's not parsed in the database. It's parsed on the client side, but we parse it in the client and then we send it to the database for execution. So we have all the other advantages that I talked about. And the numbers that we were discussing, sharing, we have tested that for PGQL as well, and PGQL has pretty much the same numbers when it comes to performance. So, and we have for SQL tools, like if it's a SQL query, you can use it natively with this tool like SQL Developer. For PGQL, we have a plugin, so you can run PGQL queries in SQL Developer. So you can pretty much do everything, but it's just recognize that it is a different language. It is PGQL, though the syntax is very similar to that of SQL. So you can get started in 19c, and that's the bottom line here. If you wanted to do something, you can just get started we can started with doing this with 19c if you have access to your 19c database. A couple of upcoming events. This one event, again, a new features in Oracle Database 23c, which actually starts in an I was about to say an hour, actually starts at noon Eastern. You could just go to the Analytics and Data Summit.org site and subscribe to this TechCast, even if you don't have time right now. If you subscribe to the TechCast, you will get a copy to the recording. And on November 16th, a couple of our customers, well, I should say Abby now works for Oracle. She used to be a customer, and now she's now working for Oracle, and Jim are going to talk about graph analytics for SQL developers. I think that will be a very interesting session as well. Again, that's November 16th, that is at noon Eastern US time. So please do visit analytics and data summit.org to sign up for this TechCast. And also we have an event, in-person event in April 2024. You can access the site to see whether you're interested in attending this session. We also have a bunch of resources, our website. We have live labs to help you get started. This uses our cloud instances, autonomous database in the cloud that literally helps you get started in minutes. You have pre-built notebooks that you can use to learn about the technology. And then we have a YouTube channel. We have blogs, and some of our developers blog on Medium as well. So thank you very much. I hope this was a useful session. And with that, let me see whether there are any questions unanswered.
We didn't have any questions today, Melly.
Okay.
No, but one just came through. No, just a thank you.
So we have some time, so we can just wait for a minute to see whether folks have any questions. Any thoughts, comments, criticisms are all welcome. Once again, please post in the Q&A panel if you have any questions. You can just give it a minute, Denise, and see whether folks have any questions. Oh, it's a question on available workshops and live labs. Yes, there are a lot of workshops focused on graph, including the 23c capabilities. So The 19C capabilities are available through autonomous database labs. Just go to the Oracle Live Labs website and search for Graph. You'll find all the labs that are available. And we also have a lab for.
I included the link to Live Labs in the answer, Melly, of chat.
Oh, perfect. Thank you. Well, if there are no other questions, thank you very much for attending. And I hope you'll keep engaged with us. We will have more and more webinars in this series as we roll out newer and newer features of Oracle Database 23C. And we always love to hear from you on what you think. So I hope this was interesting. Thank you.